Alright, in this video of my Intro to Circuits for People Who Are Not Electrical Engineers series, we will be talking about capacitors. So a very quick review. Up until this point, we have been talking about resistors, which have a resistance R measured in ohms, indicated with omega, and resistors are governed, or their behavior is described by Ohm's law, which is V equals IR, where V is voltage measured in volts V, I is current measured in amps A, and then we've already talked about the resistance. So in this video, we're going to introduce a new component called a capacitor, which has a symbol that looks like this, indicated by two parallel plates. We'll talk about that a little more in a minute. Capacitors have a capacitance, their ability to store electric charge, that is indicated with the variable C. That capacitance is measured in a unit called farads, indicated with capital F. And a quick note, a farad is a very large unit. So in practice, when using capacitors to build circuits, you are usually going to see things like microfarads, nanofarads, or picofarads. A capacitor of a farad or greater is actually very large, sometimes referred to as a supercapacitor. So again, in something like an intro circuits class, you are probably going to see capacitance values with these smaller units here. The equation that governs the behavior of a capacitor is not just an algebraic equation like Ohm's law. We are going to get more into this equation and using it in future videos, but for now I'm just going to write it down. That equation is I, the current, equals C, the capacitance, times dV dt, so the derivative of the voltage. So we now have a differential equation with a derivative in it, and depending on where you took your calculus class or the convention of the textbooks you're using, you might also see that written as CV dot or CV prime, however you prefer to indicate your derivatives, all means the same thing. I am probably going to stick with this convention in this video series, but you can use whatever works better for you. Now, if you have taken a physics class and seen capacitors before, you probably remember a diagram something like this. If not, don't worry about it, because we're just going to go over it quickly, where you have two parallel plates with surface area a distance d between them. These plates are conductive material, and there is an insulating material called a dielectric between them. That dielectric has a constant called a permittivity, indicated with the variable, I believe that's epsilon. I'm a little rusty on my Greek letters. And the equation that gives you the capacitance of this device is capacitance C equals the permittivity times A over the distance D. We don't really care about that equation in an intro circuits class because in practice, you're just going to have a kit or a shelf with a bunch of capacitors in it, and you're just going to grab them based on the capacitance rating. You don't really care what the area of the plates are or the distance between them is. There are also a ton of different types of capacitors that in practice don't look like rectangles, so while this kind of helps with a physical understanding of what's going on when you grab capacitors from a kit in a lab, they're usually going to be little circular looking things or kind of cylinder can types that will actually have parallel plates rolled up in a spiral inside them with a gap between them. So we're also not really going to be talking about the different types of capacitors and how they're manufactured, but I will mention that some of them are polarized. So if you're using these in a lab, look at the can or package and check for labels on the pins to see if they're polar. But again, that kind of goes beyond the scope of what we're going to talk about in this video, just in terms of the very introductory circuit theory. You may also see in a physics class that the unit of a farad, 1 farad, is equal to 1 coulomb per volt, but that just kind of helps if you're worried about your SI units and what all these things mean. In practice, as far as we're concerned, more capacitance means it can store more electric charge. So these conductive plates with an insulator in between them allow positive charge to accumulate on one plate, while negative charge can accumulate on the other plate. And if you are a mechanical engineer like me, the analogy that really helps here when thinking about resistors and capacitors and then inductors, which we will talk about in a future video, is to think about them analogous to a physical system where a resistor is going to be like friction or a damper, and your capacitor is going to be like a spring. So it allows you to store energy, except in this case that energy is in the form of an electric field due to separated electric charges, as opposed to the mechanical energy of stretching a spring, or elastic potential energy. Of course, the other thing to be careful about with that analogy is the symbol we use in mechanical engineering to represent a spring looks like the symbol that we use in electrical engineering to represent a resistor, so you don't want to get your analogy mixed and mix those two up. So again, don't take the analogy too literally. Think of a capacitor like a spring that stores electrical energy, and kind of think of a resistor like friction, but don't get your symbols mixed up. Now, a couple rules that will be useful for analyzing circuits with capacitors, which we are going to get to in future videos. I'm going to rewrite this equation down here, so since it got a little messy up there. One rule is what we call the continuity rule for a capacitor, and that rule, which I'm going to write down first and then explain in a second, is that voltage must be continuous over a capacitor. So you cannot, if you are looking at voltage versus time for a capacitor, you cannot have a discrete jump in voltage. That voltage must be continuous. The derivative of voltage does not need to be continuous. So again, thinking of calculus, you can have kinks in the voltage, but you cannot have jumps. And that actually arises from basically conservation of energy. If we look at this equation, in order to have a jump in voltage, that would mean that this derivative would be infinite. So the derivative of a vertical line goes to infinity. And if this derivative is infinite, then the current would need to be infinite. So to get an instantaneous change in voltage, you would somehow need to supply infinite current, which you can't do because that would require infinite power. So you, in practice, cannot actually have excuse me, an instantaneous change in voltage over capacitor. Voltage has to be continuous. That will come in handy when analyzing circuits later. The other little rule that we're going to have here is how a capacitor behaves in steady state. In other words, what happens as time goes to infinity if you have a capacitor in a circuit where the input is not changing. And in steady state, the current across a capacitor is going to go to zero, so it acts like an open circuit, and that is kind of what the circuit symbol for the capacitor itself looks like. Again, we have these two parallel plates with a gap in between them, so it looks like an open circuit. And I remember way back in high school physics, this always had me sort of confused looking at this symbol and thinking, well, how can current ever flow through a capacitor if it's blocked and there's an open circuit, right? So if I have an electron coming along and all of a sudden, well, it can't go there because there's no conductor, remember that when an electron shows up on one side of the plate, it can eject an electron on the other side of the plate and attract a positive charge here. So even though it is not literally the same electron traveling across this gap, you do still have a net flow of current. So in high school physics, maybe if you are just looking at kind of this part of it and calculating capacitance, but you haven't taken differential equations yet, so you're not looking at time-varying behavior of circuits. Many intro physics classes only look at Ohm's law, where this is just an algebraic equation and time is not a factor. So again, if you go back to the earlier videos in this series where we had something like a battery with some resistors, there was no time in this equation. Everything was just constant. And when we throw a capacitor in, now there is a derivative, we have a differential equation, and things can change with time. But in steady state, as time goes to infinity, if the inputs to the circuit are not changing, then a capacitor will behave like an open circuit with no current. And that is what we are going to talk about in the next video. So again, this video was just an introduction to capacitors. We have not analyzed any circuits with them yet. I will be adding videos to this playlist as time allows, so depending on when you are watching this on YouTube, those additional videos may or may not exist yet, but you can check out the link to the complete playlist in the video description. Thank you.